So I just wanted to do a quick update on the circuit which I had featured on this channel most recently, which was this swept-tuned audio analyzer in a box. Now I've added another quad operational amplifier on a breakout board, which for the time being is magnet snapped onto the lid of the box, so I can prototype and tweak and so on. This has a log amplifier for the x-axis, a full wave rectifier for the y-axis, as well as a video filter, and some scaling and so on. So it's carrying a pure tone right now from my pure tone generator box. And one point I'd like to make here, well, first, to prove that it's log, you can see that the width of this line is essentially nearly constant over the whole band. And another thing I'd like to point out is just how little variation in the response there is. When I was first analyzing this thing, I was running the tone in, well, just using my smartphone as a signal generator for square waves and whatever. And it has well over 6 dB of ripple over the audio band, and maybe 10. And I was ready to blame that on my analyzer. But it's nice to have a closed loop, precise amplitude tone with which you can test it, and the frequencies almost quite line up. You can see I'm pegged here at about 10K, which is the caps I put in here most recently. That's where it stops. So yeah, I think that's mostly a good rundown of what's going on. I guess I will have this little switch here, which I can push to engage the video filter. The only problem is that it has a recovery because it's a capacitor. It has some charge. When this sweep restarts, I lose the half a kilohertz at the end. And but anyways, this is the video filter here, and it's pretty cool. Depending on what you're looking at, it's actually a pretty good way to look at it. Although, because the filter integrates it, it never touches down quite to zero here, and you lose your zero reference. Whereas without the video filter here, you have your zero pegged. The other thing, which I don't know if it's visible or not, I'm going to turn this up to blinding, blinding levels. You can see that the trace kicks off and it's hitting the rail as it recovers, and it drops down to form this loop. And so the way I had it before, when it was sweeping back up, it was just also populating the bins on the way back up, but which is not reasonable because it's an irregular and way too fast sweep. So it was just making for a very noisy display. This is really nice, and it gives me a kind of a cool frame to look at this. And so normally I would have it set up so that those are, just right on the edge of the screen, sort of thing. So with these mods, especially the log in frequency, I'm not going to take you through a whole demo of this again with square waves and whatever. But, well, actually, let's see. Hang on. Do I have something interesting? Let's see. There's a cal signal over here. Let's see if I can get that. This scope. This is the guest star for today's episode, this Leader LBO 310A, which is sort of a joke of a scope. This is my very first oscilloscope, which I purchased for $20. It has a bezel missing, some burns in the phosphor. It was covered in paint and weird coffee stains, and it needed everything about it fixed. But I'm glad I picked it up because it really worked for me. One of the funny things is the banana jacks here on the front. I've actually installed a BNC on the back of it, and I've run coax through it up to the amplifier in there. And there's a little compensation capacitor that I added to make it so that that BNC is actually a good input. That made these banana inputs even worse. But oh yeah, and the other thing is that it's, well, anyways, whatever. Enough about that. Uh, yeah, I guess this isn't the fundamental here. I'm pretty sure because this is I think it's 500 hertz. So let's see if I slow it down. I'll have to rescale it. Yeah, so I got this out of control. That's not bad. Oh, I'm messing with the attenuator. And because it's so slow, it's kind of, there we go. It's pretty cool. I don't know. Anyways, you get the idea. You have to get it to look nice. You have to kind of fit whatever you're looking at. But, oh yeah, and this is still deafeningly bright. So I think that's it. Yeah. Well, I guess I'll show you these circuits. Why not? So we got here the precision full wave, which I put together just because I had the traces on that board were very similar to this, so I didn't have to do much to just implement this. And how it works is I've got a nonlinear cell over here, which shuttles positive into positive and negative into negative, but it does so with an exponential because these diodes. So I'm compensating that exponential with this cell up front, and well, it's pretty easy to analyze. In the long run, for large voltages, these diodes are shorted effectively, and so it's basically a unity gain follower. And so, it's a unity gain follower that jumps past the threshold voltage of the diodes. It's one way to look at it, an imprecise way. But anyways, this isn't the typical full wave circuits. Why I thought it was worth pointing out. The other thing is the log amp is I needed non-inverting, so it's a regular log amp with a blue LED as the nonlinear element, and I'm also leaking a little positive current into here, which really jams it to the negative rail when there's no input, and so it really does look like a nice log, and then I'm putting some gain and also leaking some more current into here, shifting it to get it scaled so that I have very nearly the full rails of a nice linear thing. Depending on how the sweep is set, the sweep moves around on that. So, but the reason for that is because what I'm planning on doing is um, actually having this guy carrying my frequency domain and this guy in the time domain, because this is a great scope. This keeps pace with normal scopes. Very nice trace this on this Gould. But yeah, I just found out that the H input. Well, okay, whatever. We'll talk about it another time. That's it for now. Thanks for watching.